Hey guys, tonight we are going on the longest journey imaginable. A gentle drift through the 13.8 billion years of cosmic history that had to unfold perfectly just so you could be here, listening to this story. You are going to trace your very being back to the moments before stars existed, realizing that every atom in your body is a piece of ancient, recycled stardust. As you settle in, picture the vast, dark emptiness that existed just milliseconds after the Big Bang. It's quieter than you can possibly imagine. The universe is an infinitely dense, hot speck, and then a monumental, beautiful expansion. You aren't experiencing this heat or pressure. Of course, you're a silent observer floating alongside time itself. Initially, everything is simple. Just the lightest elements, hydrogen and helium, swirling in a uniform, massive cloud. But gravity, that tireless sculptor, begins to pull these clouds together over hundreds of millions of years. You watch as the first gigantic, short-lived stars ignite true cosmic factories. These stars were colossal, beautiful, and utterly brutal. Inside their unimaginable pressure cookers, the simple hydrogen and helium atoms were forged into heavier elements: carbon, oxygen, nitrogen, the very building blocks of life. Without the death of these first stars, you wouldn't exist. They had to live, create, and then explode into supernovae, scattering their elemental gifts across the nascent galaxies. It's a sobering thought. You are literally the ashes of dead stars. The oxygen you breathe, the iron in your blood, all of it was forged in a stellar furnace that winked out billions of years ago. You probably wouldn't survive to see the end of this era. The cosmic radiation levels and the sheer heat from the first stars were overwhelmingly intense. But you float on, observing these celestial fireworks. This period, known as the Dark Ages, ends when enough stars form to reionize the neutral gas. You see the universe slowly beginning to glow again. Think of the irony. To get the complexity of life, you first needed the violent destruction of the universe's pioneers. Historians still debate whether the very first stars formed from dark matter halos, which would mean that this mysterious, unseen scaffolding was also essential for your existence. That's a curious detail, isn't it? The stuff we can't see had to gather the stuff we can see into star-forming clouds. It's like the universe's stagehand was wearing an invisibility cloak. One solid historical fact we rely on is the cosmic abundance of elements. We know the proportions of elements found in the sun, in meteorites, and here on Earth, and these proportions perfectly match the predicted yields from stellar nucleosynthesis and supernovae. Your body is a precise, time-delayed chemical signature of the early cosmos. Now, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're listening from and what time it is for you down in the comments. It's comforting to know we're sharing this cosmic journey across different time zones. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's drift into tonight's story together. As the eons pass, the scattered stellar dust begins to coalesce into galaxies. You watch your own Milky Way spin up, a gigantic, organized disk of billions of stars, one of which your own sun is destined for greatness, simply because it's not too big and not too small. Goldilocks was already at work, long before your solar system even began to form. That glowing, churning spiral of stars is the Milky Way, your future galactic home. Within one of its quieter, unassuming arms, you see a small, dense cloud of gas and dust begin to stir, pulled inward by its own gravity. This is the solar nebula, the cosmic womb from which your entire solar system will be born. It's a slow, majestic process that takes millions of years, almost too leisurely to perceive. You watch as the central mass compacts and heats up, glowing a brilliant orange. This is the proto-sun, and it's surrounded by a flat, spinning disk of material. It looks a bit like a cosmic pizza spinning in an oven, and you can't help but be reminded of those old science diagrams from school. Within this disk, The gravitational dance is meticulously choreographed. Tiny dust grains stick together, forming pebbles. These pebbles grow into rocks, then boulders, and then planetesimal small, embryonic planets. The inner solar system, closer to the hot young sun, is a realm of fiery collisions and rocky worlds. You see the early Earth, a barren sphere of molten rock, constantly bombarded by debris. But farther out, where temperatures are colder, you watch the giant gas planets begin to form. Jupiter, a magnificent, swirling Goliath, is a particularly important player in this cosmic drama. It's so massive that it acts like the solar system's bouncer, using its immense gravitational pull to slingshot dangerous comets and asteroids away from the inner planets. Historians still debate whether the very existence of Earth's stable, long-lived climate required Jupiter's precise orbital position to clear out the chaotic cosmic debris. It's a compelling thought. Our planetary bodyguard was an absolute requirement for our continued existence. Jupiter's influence isn't just about protection. One solid historical fact is that its gravitational field also shaped the asteroid belt between Mars and Jupiter. Without the giant planet's interference, that belt might have coalesced into a fifth rocky planet, but its constant gravitational nudges prevented the material there from ever clumping into a single body. This means that a massive reservoir of potential threats was kept from becoming a single, organized planet that could one day collide with Earth. Talk about a cosmic lucky break. As you float through this era, you witness a curious or lesser-known detail of solar system formation: the Grand Tack hypothesis. This theory suggests that Jupiter didn't just stay in one place. It may have migrated inward, toward the Sun, sweeping up or scattering a huge amount of material, and then reversed course, migrating back out to its current position. A perfect little orbital pirouette that dramatically influenced the final architecture of the inner planets. It's a bit like a toddler rearranging all the furniture in a room before deciding where to put their toys. This gentle but powerful gravitational choreography created the perfect environment for a small, rocky planet like Earth to exist in the habitable zone. A little slice of real estate where liquid water could one day pool on the surface. You're watching billions of years of cosmic choreography unfold, all for the benefit of this tiny blue marble. You are now fixed on the violent spectacle of the early Earth, a mere 4.5 billion years ago. The planet is still a churning magma ocean, incandescent and unforgiving. This period is dominated by the Great Accretion, where planetesimals constantly smash into the nascent Earth, adding mass and releasing tremendous heat. Imagine a cosmic demolition derby, except the prize is the most beautiful planet in the universe. This constant barrage is necessary, of course, because it's the only way to build a world this size. Then comes the event that shapes everything: the Theia impact. A Mars-sized protoplanet, named Theia, slams into the early Earth. The collision is so catastrophic that it melts and vaporizes huge sections of both bodies, blasting molten rock and debris into orbit. You watch this fiery ring of material quickly coalesce, forming the Moon. This is a solid historical fact. The Moon formed from a massive impact, and the resulting debris quickly gathered in orbit. The Moon's creation is a moment of perfect cosmic convergence. Its sheer size relative to Earth stabilizes our axial tilt, preventing wild, chaotic climate swings that might have sterilized the planet long ago. Without the Moon's steadying hand, life would have faced an impossible evolutionary challenge. As the Earth slowly cools, a critical question arises: where does the water come from? Our planet was formed close to the Sun, in the dry, rocky zone. Most of the Earth's original, volatile materials were probably baked away. Historians still debate whether the majority of Earth's water arrived from icy comets impacting the surface, or from volatile-rich C-type asteroids that were later scattered inward from the outer solar system by the gravitational influence of Jupiter and Saturn. It's a curious, or lesser-known detail, that analysis of the deuterium to hydrogen ratio in certain meteorites suggests they are a better match for Earth's ocean water than most comets. Whatever the exact source, you watch as billions of years of bombardment deliver the precious liquid. The first rain begins to fall. It's not a gentle shower, but a prolonged, epoch-defining downpour that lasts for millions of years. As the surface temperature finally drops below the boiling point of water, the steam atmosphere condenses, filling the deepest basins and forming the first incredibly hot, iron-rich oceans. You wouldn't survive this rain. It's acidic and steaming hot, and the atmospheric pressure is immense. Yet, in this violently assembled, water-drenched environment, the stage is set. This planet now has the raw ingredients, heavy elements from dead stars, a stable orbit thanks to a nearby giant planet, a steady tilt thanks to its huge moon, and vast oceans of liquid water. Now, if only something happened in that water. I mean, come on, you've done all this hard work. Universe, let's see some results. The stage is indeed set, and you are floating within the warm, chaotic soup of the early Earth oceans, roughly 3.8 billion years ago. This is the era of abiogenesis, the great mystery of how non-living chemicals transition into self-replicating life. The oceans are dark, mineral-rich, and teeming with volcanic activity. Look closely near the hydrothermal vents, those deep-sea smokers where superheated, mineral-laden water bursts from the seafloor. These vents are shielded from the harsh ultraviolet radiation that still batters the surface, and they offer steep temperature and chemical gradients, acting as natural reaction chambers. Imagine the sheer concentration of energy and raw materials. Simple organic molecules, like amino acids and nucleotides, forming spontaneously under these extreme conditions. This is a solid historical fact. Laboratory experiments like the famous Miller-Urey experiment have successfully demonstrated that key organic molecules can be created from inorganic precursors under simulated early Earth conditions. The building blocks are ready, but they need assembly instructions. The trickiest part is moving from simple molecules to something that can self-replicate and evolve. You are watching a curious or lesser-known detail unfold: the RNA world hypothesis. Many scientists believe that RNA, ribonucleic acid, which is both a carrier of genetic information and a catalyst, an enzyme, or ribozyme, was the first lifelike molecule. Before the double helix of DNA, there was this versatile single strand. It's like the universe first invented a Swiss Army knife that could both store data and perform tasks. It solved the chicken and egg problem of genetics. Which came first, the DNA or the protein? Historians still debate whether the first sparks of life ignited in the deep-sea hydrothermal vents, or within shallow surface pools that underwent repeated cycles of wetting and drying, concentrating the organic compounds on mineral surfaces. Each environment offers a compelling argument for the necessary energy and concentration mechanisms. You, the silent observer, are watching molecular chaos slowly find order. The earliest forms of life you see are microscopic, simple prokaryotes, cells without a nucleus. They are tiny, robust bubbles of membranes surrounding their self-replicating RNA or DNA. They are essentially little survivalists in a hostile world. It took a while to get here, right? Billions of years of cosmic forging, planetary collision, and water delivery, all culminating in a tiny, wiggling, lipid bubble. If you could zoom in, they'd look like miniature, slightly disorganized water balloons trying to have a very important conversation with themselves. This is the most critical convergence point so far. The moment that physical chemistry gives way to biological evolution. The universe had perfected the ingredients, the temperature, and the container. And now, Finally, the process of life itself can begin its own iterative, relentless climb toward complexity. The stage is set for the long reign of the single-celled organism, a reign that will last for 2 billion years. For nearly 2 billion years, you watch the world remain a microbial monoculture. The dominant life forms are tiny prokaryotes, little bags of living goo surviving in a world without free oxygen. It's an invisible, microscopic empire flourishing in the dark, warm oceans. But a quiet revolution is brewing, led by a humble little group of organisms called cyanobacteria. They discover a new, incredibly efficient way to make food: photosynthesis. They figured out how to use sunlight, water, and carbon dioxide to create energy, releasing a waste product that will utterly transform the planet: oxygen. You see, the first tiny bubbles of this new, corrosive gas rise from the surface of these ancient bacterial mats. This is a solid historical fact. The rise of atmospheric oxygen began with cyanobacteria, but this wasn't a gentle, welcome change. To most of the life on Earth at the time, oxygen was a deadly poison. It was a potent oxidizing agent that would tear apart the complex organic molecules they were made of. This event, known as the Great Oxidation Event, or sometimes the oxygen catastrophe, was the first and greatest pollution crisis in Earth's history. It was a mass extinction of unimaginable scale, as trillions upon trillions of anaerobic bacteria died off. You're watching a planetary remake unfold in real time. The dissolved iron in the oceans reacts with the new oxygen, creating huge deposits of rust that settle on the seafloor, forming what we now call banded iron formations. This is a curious or lesser-known detail. These rust-colored layers are a literal geologic record of the planet's first gasp of oxygen. Imagine the scale of it all. Enough rust to fill entire mountain ranges, all created by tiny, single-celled life. It's a beautifully silent monument to a biological war. Historians still debate whether the initial rise in oxygen was a gradual, steady increase or a series of pulses that caused multiple glaciations as the greenhouse gas methane was oxidized away. Whatever the exact pace, the oxygen content of the atmosphere slowly but steadily rose, paving the way for a whole new kind of life. Oxygen, once a killer, became a powerful new source of energy for the organisms that could harness it. It's the ultimate, if you can't beat 'em, join 'em story. The tiny survivors and their descendants evolved new metabolic pathways to use this energy, which unlocked the possibility of larger, more complex bodies. The world is finally changing colors. The air becomes breathable, the skies clear, and a new evolutionary arms race is about to begin. You've just witnessed a planetary scale reset, all thanks to some incredibly determined microbes. Remember that great planetary reset, the one driven by oxygen? That catastrophe didn't just change the air. It forced life to get incredibly creative. You are now entering the era known as the Proterozoic, a time spanning about 2.5 billion to 541 million years ago, where the major convergence is happening not just around the cell, but within it. The availability of oxygen, that powerful fuel, meant that cells could afford to become much, much bigger. You watch as the simple, unorganized prokaryotes, those basic bags of genetic material, begin a revolutionary partnership. This is the moment a small bacterium gets engulfed by a larger prokaryote. But instead of being digested, it remains a resident, becoming an internal energy factory. This is the foundational event of the eukaryotic cell, the type of cell that makes up you, me, trees, and almost every visible life form on Earth. This engulfed bacterium becomes the mitochondrion, the powerhouse of the cell. This specific event, the endosymbiotic merger, is a solid historical fact, evidenced by the fact that mitochondria still retain their own distinct, circular DNA and reproduce independently, almost as if they were still separate bacteria living inside your cells. This new eukaryote is a huge leap in complexity. It has a nucleus, a safe, dedicated library for its genetic blueprints, and all those specialized organelles. Suddenly, single cells can be thousands of times larger than their simple ancestors. This complexity unlocks the ability to form truly multicellular life. You see the first clumps of cells sticking together, communicating, and specializing their roles, some for feeding, some for reproduction, and some for defense. It's the first great team-up in history. Now, observe the curious and lesser-known detail of sexual selection. For the first billion or so years of life, reproduction was simple, cloning, asexual. Every offspring was a perfect copy of its parent. But once eukaryotes arose, they stumbled upon the messy, beautiful invention of sex. This process, where two parents contribute genetic material, constantly shuffles the deck. This is why you don't look exactly like your siblings. This genetic mixing creates rapid variation, allowing life to adapt and evolve at a dizzying pace. It was a huge risk. Why mix a perfectly good set of genes with someone else's? But the payoff was exponential evolution. Historians still debate whether the emergence of true multicellularity was driven primarily by environmental changes, such as falling nutrient levels requiring cooperation, or if it was simply a natural byproduct of the genetic control complexity afforded by the new eukaryotic architecture. Regardless, you are witnessing the moment life shifts from a slow, steady march into a frantic, diverse sprint. Everything you know about evolution, from Darwin's finches to your own opposable thumbs, is predicated on the genetic engine of sexual reproduction. It's like the universe finally gave life a turbo button. You have now reached a pivotal moment in Earth's history, a time of extremes that directly precedes the explosion of recognizable life. The planet, having finally evolved complex eukaryotes, decides to throw a planetary party of ice. You are about to experience the Snowball Earth episodes, vast, deep freezes that occurred between about 720 and 635 million years ago. Imagine this. The entire globe, from pole to equator, is encased in ice, possibly a kilometer or more thick. This is a solid historical fact, evidenced by diamictites, glacial deposits found even in rocks that were near the equator at the time. You float above this frozen wasteland, seeing only white reflective ice. Life survives only in tiny pockets, perhaps near deep-sea hydrothermal vents, or in microscopic liquid pools trapped beneath the ice where geothermal heat persists. This deep freeze, counterintuitively, sets the stage for the greatest surge of life the planet has ever seen. The theory is that the glaciers ground up immense amounts of rock, and when the Earth finally thawed, triggered by volcanic activity, slowly accumulating carbon dioxide, CO2, went for the Fenton and it for thems, and upgrading with places, and it for thems, with that dividend by. In the atmosphere, these rocks released massive amounts of nutrients into the oceans. The sudden influx of food, combined with the higher oxygen levels left over from the Great Oxidation Event, remember that earlier catastrophe, created the perfect, nutrient-rich environment. Watch the ice melt, and the geological equivalent of a dam breaking occurs. This leads directly into the Cambrian explosion, roughly 541 million years ago. Suddenly, in a relatively short span of about 20 million years, almost all the major body plants, phyla, that exist today appear in the fossil record. You see creatures with hard shells, complex eyes, jointed legs, and specialized appendages. Before the Cambrian, life was mostly soft, microscopic, or simple tubes. Now, you see the bizarre, five-eyed Opabinia, and the mighty, segmented predator, Anomalocaris. It's a spectacular, sudden diversification. Like the universe hit the fast-forward button on evolution. It's truly a curious or lesser-known detail that many of the Cambrian organisms, though complex, represent evolutionary body plans that ultimately went extinct, like failed prototypes on the path to modern life. Historians still debate whether the Cambrian explosion was a truly rapid biological event, a sudden invention of hard parts and predation, or merely a sudden appearance in the fossil record, because life had finally evolved shells and skeletons, which preserve well. Did the life suddenly appear, or did it just finally decide to wear armor? You watch this ancient seabed, realizing that the convergence of cosmic stardust, planetary water, microbial oxygen, and global deep freezes were all necessary preconditions for this spectacle of complex, macroscopic life. All those earlier, agonizing steps, the fusion of cells, the poisoning of the atmosphere, were just practice for this evolutionary sprint. You've witnessed the spectacular diversity of the Cambrian seas, a world teeming with strange, shelled, and segmented creatures. But for hundreds of millions of years, the land above the waves remained largely sterile, a harsh, desolate environment blasted by sun and wind. The next great convergence you observe is life's bold leap, the colonization of the terrestrial world, starting around 470 million years ago. For life to leave the comforting buoyancy and UV filtering properties of the water, two major preconditions had to be met. First, the land needed soil, a process that began with tiny microbes and fungi, forming symbiotic relationships, breaking down rock and creating the first rudimentary organic ground. Second, and most critically, the planet needed an atmospheric shield. Remember that toxic, corrosive oxygen that the cyanobacteria produced back in Section 5? That gas, thanks to the sun's UV radiation hitting it in the upper atmosphere, finally transformed into ozone. The slow thickening of this ozone layer, a solid historical fact, created the necessary protection, shielding the surface from sterilizing ultraviolet radiation. Without this invisible sunscreen, land life was simply impossible. With the shield in place, you watch the ancient relatives of modern plants, small, moss-like organisms, courageously creep out of the water. They face immediate challenges: how to prevent desiccation, drying out, and how to support their own weight without the water's lift. They develop cuticles, waxy coatings, to retain moisture, and vascular tissue, internal plumbing, to transport water and nutrients, allowing them to grow taller and conquer the vertical space. This is a curious, or lesser-known detail. The first forests of the Devonian period weren't necessarily tall, woody trees like today, but often bizarre, giant fungus-like organisms or thick stands of primitive club mosses, completely changing the landscape and the chemistry of the soil. The animals soon follow the plants, drawn by the new abundance of food and habitat. The fishes, which had evolved jaws and skeletons, find ways to use their fins for crawling. You observe the transition of creatures like Tiktaalik, often called a fishapod, a crucial missing link showing both fish and tetrapod, four-limbed vertebrate, characteristics. Historians still debate whether the initial transition of vertebrates from water to land was driven by the need to escape predators in crowded, oxygen-poor swamps, or by the availability of new food sources, like insects, on the exposed land. Regardless of the initial motivation, this move fundamentally changed the course of evolution. The gravity of the land environment favored stronger skeletons and powerful musculature, paving the way for reptiles, dinosaurs, and ultimately, us. You realize that your own internal structure, your lungs, and your ability to stand upright are all an ancient, triumphant echo of that moment, when an aquatic creature first dragged itself onto the shore. You are now watching the steady march of life on land accelerate and diversify. The forests become vast, dominated first by giant ferns, and then by the first seed-bearing plants, the gymnosperms. Reptiles evolve, becoming masters of the terrestrial world, culminating in the reign of the dinosaurs. It seems like life has finally achieved its peak complexity and stability. But in this story of perfect convergence, you must understand that creation often requires destruction. You are about to witness the universe's most brutal editing tool, mass extinctions. Over the course of Phanerozoic eon, life endures 5 great extinctions. Think of them as necessary, violent planetary resets. The most devastating of these is the Permian-Triassic extinction, about 252 million years ago. This is a solid historical fact, often called the Great Dying, as it wiped out an estimated 96% of all marine species and 70% of terrestrial vertebrate species. The world became a biological desert, likely triggered by massive volcanic eruptions in Siberia that destabilized the climate through greenhouse gases and acid rain. It was the moment the evolutionary slate was nearly wiped clean. Why is this destruction essential to your story? Because these mass extinctions, though terrifying, cleared the ecological niches, allowing previously small, unassuming groups to explode in diversity. For example, the Permian extinction set the stage for the dinosaurs to become dominant in the Mesozoic era. Then, 66 million years ago, the Cretaceous-Paleogene (KPG) extinction occurred, the event most famous for ending the age of the dinosaurs, caused by a massive asteroid impact in the Yucatan Peninsula. You observe the chaos, the impact, creating a global firestorm, followed by a long, dark cooling period caused by dust blocking the sunday. Amidst this destruction, you see the quiet survivors, the small, furry, often nocturnal creatures known as mammals. They had existed for tens of millions of years, often scurrying in the shadow of the giant reptiles. This is the curious or lesser-known detail. The largest pre-KPG mammal was probably no bigger than a badger. Only after the dinosaurs were gone could mammals seize the opportunity. Historians still debate whether the mammals' ability to survive the KPG extinction was due to their small body size and generalist diets, or if their warm-bloodedness, endothermy, gave them an advantage in the post-impact cooling. Regardless, the extinction cleared the table, allowing the handful of surviving mammalian lineages to rapidly diversify and fill the vacant niches. You realize that without the violent destruction of the dinosaurs, a moment of catastrophic cosmic convergence, the age of mammals, and the rise of primates would never have happened. You owe your existence to that enormous space rock. You stand in the Cenozoic era, the age of mammals, a world radically reshaped by that final devastating asteroid impact. The survivors, the small mammals, begin their rapid evolutionary journey, taking advantage of the diverse ecosystems now open to them. For the last 66 million years, you observe the steady refinement of the mammalian body plan, leading to primates, and eventually to the lineage that leads directly to you, the hominids. The final, most astonishing convergence is not a physical change to the planet, but an internal, neurological one, the birth of consciousness. You watch as early hominids like Australopithecus emerge in Africa, adapting to the changing climate, which pushes them out of the forests and onto the open savannas. A crucial solid historical fact here is bipedalism, walking on 2 legs. This shift, which happened over millions of years, freed the hands for tool use and carrying, but also, critically, allowed for a clearer line of sight over tall grasses. It was a trade-off that defined our future. As the environment continues to fluctuate, the hominid brain begins a process of exponential growth. You watch Homo habilis create the first sophisticated stone tools, showing early signs of planning and dexterity. Then comes Homo erectus, who masters fire, a curious or lesser-known detail. Fire didn't just provide warmth and protection. It allowed them to cook food, which made the nutrients more easily digestible. This meant they didn't have to spend as much time chewing. And, crucially, it provided the stable, high-energy fuel required to power a larger, metabolically expensive brain. The final surge occurs with the emergence of anatomically modern humans, Homo sapiens, roughly 300,000 years ago. What truly sets this lineage apart is not just the brain size, but the development of complex language, abstract thought, and self-awareness. This rapid, recent evolution is the culmination of everything that came before. All the perfect, near impossible astronomical, chemical, and geological conditions. The stable sun, the heavy elements, the liquid water, the oxygen, the stable climate, the mass extinctions were necessary to create a vessel capable of knowing itself. You are witnessing the development of a mind capable of looking back at the entire 13.8 billion year chain of events and understanding it. You, the listener, are the physical realization of the universe's ability to self-reflect. Historians still debate whether the rapid development of human consciousness was primarily driven by social pressures requiring complex communication, or if it was an evolutionary adaptation to climate instability requiring abstract, long-term planning and problem-solving. Whatever the trigger, the result is that you have been created, a tiny pocket of stardust that is now conscious of its cosmic origins. You are the perfect convergence, the universe made aware. The long journey now begins to slow. Feel the vast, overwhelming scale of 13.8 billion years gently recede. You can let go of the swirling nebula, the violent planetesimal impacts, and the silent, world-altering march of the cyanobacteria. Those images of fire and ice, of microscopic battles and dinosaurian reigns, are now just wisps of history, fading into the comfortable darkness around you. The constant, relentless pressure of gravity and evolution that drove this story, the necessity of that single, stable star, the violence of the moon's birth, the toxic gift of oxygen, all of it has led to this quiet moment, right here, right now. There is no more striving, no more colliding, no more running from the ice or the predators. There is only the stillness of the present. Allow your awareness to soften, no longer straining to trace the lineage of your atoms back to that first stardust. Let the sounds of the room, the gentle background hum of the fan, and the soft rhythm of your own breath bring you fully into this single, safe point in time. The universe has done its work. Every step was taken so that you could exist and, just for a moment, understand the incredible, fragile miracle of your being. You are a culmination, a brief, beautiful flicker of self-awareness, born from the perfect, impossible convergence of everything. Rest now. There is nothing left to achieve but peace.